To my lab 8, and let's just get right into it. This is my circuit. I have my LED, and as I turn it, it'll turn on, and then as I get halfway through, it turns. You can't see it very well, but it's actually dimmed, not completely off, and it gets darker and darker, which aligns with what we expect from our LED and from our op amp when we change the voltage difference. For exercise 1, we have this circuit, and the way I analyzed it is that I said V plus is equal to V input, and because V plus is equal to V minus, because of the op amp, V minus is also going to be equal to V input. Since there is no current flowing through the op amp, we can do nodal analysis on this node without considering this wire, which gives us that V out is equal to V in times R1 plus R2 over R1. This is the circuit I have for example 2, and this is what I get when I code and put it on processing. I'm going to increase V in, and you can see that V negative follows it. V out is also following it. However, you can't see it because green and blue are right on top of each other. You can see that until I reach about 2 volts, they don't follow each other, and that was expected because of the AV that we learned about in one of the pre-lectures. This is my circuit for example 3. You can see my code in the back. Not much has changed, which you'll see in the code section, but this is what I have in processing, and as I change the voltage, you can see green and white are following each other. I guess green is following white, but blue is bound between 2 and 4 volts, and it's inversely proportional to green. We expected this exact scenario because there's supposed to be a negative 10 gain. Again, blue is bound between 2 volts and 4 volts, which is expected. We also see that when blue plateaus, green also stalls where it is, which is expected again when you do the calculations. Example 4. We end up doing nodal analysis over here because we know that V plus and V minus are equal to 0. We get this equation where V in is equal to negative R over the impedance of C times V out. We rearrange it and we find this equation. We know that J times omega is equal to the integral of V in with respect to time because of work we did in lecture. So this is the final equation. If we plug in the resistance and the capacitance, we find that this is the equation that we find, and negative 21.27 is the gain or loss, depending on which way you're going. Here, this is the circuit that we have, and this is what it's giving us. As I increase the voltage, you can see that the V out is changing based on the time. And again, as I go down, it changes by integrating based on time.